Thank you, and thank you for the opportunity to take part. That's interesting online conference.
Yeah.
And I would like to talk a few words about the Jeloshinsky-Moria interaction and the effect of the Jeloshinsky-Moria interaction on the magnetic anisotropy. Okay. The research mainly was done at the Technical University at the Budapest in the Department of Theoretical Physics. So, at the beginning, I would like to summarize very briefly something about the spin reorientation transition and the behavior of the Jeloshinsky-Moria interaction and the effects relayed on the Jeloshinsky-Moria interaction. And then I would like to show you our results on some Monte Carlo simulations on that system. So, the magnetic anisotropy is due to the relativistic effect, mainly the spin-orbit coupling. And this determines the orientation of the magnetization in a ferromagnetic system. For thin films, it has even more important role because in the lack of the magnetic anisotropy, there would be no long-range order according to the Mermin-Wagner theorem. So for thin films, the magnetic anisotropy have a key role in the formation of the long-range order. Okay, well, there are different kinds of magnetic anisotropies. We can have a magnetocrystalline anisotropy, we can have the shape anisotropy, we can have surface anisotropy, and so on. And the different kind of magnetic anisotropies has a different temperature dependence. And the competition between the different kind of anisotropy may result in a thickness or temperature dependent reorientation. So it's well known that some, for example, one of the well-known example is the iron layers on a gold 001 surface. While the iron, the gold is has an FCC structure, the iron has a BCC structure, but it can grow epitaxially on a surface of the 001 surface of the gold, and a monolayer or a double layer of iron on a gold has a normal to plane orientation, and if we further increase the film thickness, the orientation of the magnetization turns into the plane. But also there are several experiments which shows that there is a temperature-driven reorientation. So at low temperature, the system has, for example, a normal to plane orientation. Just like in that case, this is an iron thin films on a silver 001 surface. At low temperature, it has a normal to plane orientation. As the temperature is increasing, the orientation of the magnetization turns into the plane. There are several other examples showed here. So it's a well-known process. It's a well-known phenomenon. Okay, so if you would like to modelize such a system, we can use a simple model. In our case, this is it's a simple Heisenberg-like model where we have a nearest neighbor coupling, and we have two competing anisotropy. One, which it's somehow simulate some two-side anisotropy. For example, which originates from the dipole-dipole interaction, but it's a consequence of the symmetric anisotropic exchange. And there is, which this in our case, this prefers the in-plane orientation, and we have an on-site anisotropy and uniaxial anisotropy, which prefers the normal to plane orientation. That direction is just refers the normal to plane orientation. We can calculate the free energy as a function of the orientation of the magnetization. We can do it on a different way. We use a metadynamic simulations. We use a Monte Carlo simulation and use the metadynamics. The metadynamics, it's a similar method to some, it's a member of the class of the biasing potential method. For example, the umbrella sampling is also a similar method. Using the metadynamics, we can explore the free energy surface along some special direction, which called a collective variable in the language of the metadynamics. So we can find this biasing potential, and this biasing potential is shown in the inset. In our case, in the case of a monolayer, it's just a parabole, and what we can see that the curvature of the parabole changes its sign at the transition temperature, so we can detect a temperature-driven reorientation at a reorientation temperature. So this anisotropy energy, well, it starts at a given value and of course goes to zero, because at the paramagnetic phase there is no anisotropy, of course, but at a given temperature it changes its sign. Okay, but it was a simple Monte Carlo simulation using some parameter. Okay, so the Jalushinsky-Morier interaction, we can extend our model with the interaction with the chiral interaction when we have a Jalushinsky-Morier vector, TIG, and the cross product of the interacting spins. In our case, this is a classical model, so the spins, simple unit vectors, just parallel to the orientation of the magnetization at a given site. Okay, so if we have a ferromagnetic system, all the spins are parallel to each other, and that's why the Jalushinsky-Morier interaction has no contribution to the energy of the system. So we don't expect any effect of the Jalushinsky-Morier interaction if we have a ferromagnetic system. Well, but if we have a non-collinear magnetic system, we can have so the Jalushinsky-Morier interaction can have an impact on the magnetic structure. For example, it can decrease the energy of the spin spiral, and the spin spiral state can be the ground state of the system. Or when we have a domain valve, it changes, it determines the orientation of the domain valves. And it's one of the most important things that in the presence of the Jalushinsky-Morier interaction, we can have a skyrmions. I think skyrmions first detected, the magnetic skyrmions first detected in the case of the manganese silicide in a bulk system, but it's also present on the thin film system. It's a well-known example. It's the iron on the top of the iridium-111 surface with a palladium cap layers. At low temperature, here we can see that we have a spin spiral state. This is a spin polarized STM image on the right hand side, and this is we can see this pattern here. The strides here belongs to the spin spiral state. If we consider this spin spiral state, if we increase the external magnetic field, some skyrmions will appear, and if we further increase the external field, we will get a skyrmion lattice. And of course, if we further increase the external field, we will have a uniform sample, we will get a ferromagnetic state. So, but if you have a ferromagnetic system, we don't expect any impact of the Jalushinsky-Morier interaction on the system. Okay, but since we have a fluctuation of the spin. In this example, we have a simple centered rectangular lattice. In the experimental example, we will study the iron on a tungsten 110 surface, and the iron monolayer has just such a centered rectangular lattice at K. Well, in that case, due to the symmetry of the system, we can have a Jelshinski-Moria vector between the nearest neighbors here, denoted by that green arrow here. Of course, if we increase the temperature, suppose that the direction of the ferromagnetic orientation is just, in that case, parallel to the longer side of that rectangle here. If we consider the two spins, S1 and S2, it is just precessing around the direction of the ferromagnetic orientation. And due to this precession, the fluctuations is just perpendicular to the orientation of the magnetic, to the ferromagnetic orientation. And if we consider the fluctuations, the cross product of the fluctuation is just parallel to the direction of the Jelshinski-Moria vector. So due to the fluctuations, even in the case of a ferromagnetic system, the Jelshinski-Moria interaction can have an impact on the energy of the system. Of course, if the temperature is low and the fluctuations are negligible, this contribution should go to zero, and at the paramagnetic phase also it should be zero. But at finite temperature, there should be a contribution due to the Jelshinski-Moria interaction, even in the case of a ferromagnetic system. So if we did a simple simulation, then we have that centered rectangular model. We have just a Jelshinski-Moria interaction between the nearest neighbors. We have a nearest neighbor exchange, and we have some biaxial anisotropy denoted by L lambda x and lambda y. Okay, and we calculated the free energy difference between the in-plane and normal to plane orientations using this biasing potential method. And the black curve belongs to the anisotropy energy, neglecting the effect of the Jelshinski-Moria interaction, so without this last term. And if we turn Jelshinski-Moria on, we got a deeper energy, the deeper anisotropy energy. And this is just the difference is depicted on the figure on the right-hand side. And we can see that if the temperature is low, the fluctuations are small, and there is no contribution of the Jelshinski-Moria interaction to the anisotropy. If the temperature is increasing, we will get an increasing contribution, and finally it goes to zero at the paramagnetic phase, of course. So, okay, let's see. Okay, this is the concrete model for the iron double layer on the tungsten 110 surface. Okay, so we can have the exchange interactions, the Heisenberg exchange. We can have a Jelshinski-Moria interaction. We have just this symmetric anisotropic exchange and a biaxial anisotropy due to the symmetry, the C2V symmetry of the system. Okay, and the first three terms can be just written in a more compact form when we can introduce a tensorial exchange coupling between the classical spins. This is denoted by J here. And of course, this is a 3x3 tensor, and we can decompose it. This trace, 1/3 of the trace is just the isotropic term of the exchange couplings. The anisotropic part is responsible for the Jelshinski-Moria interaction, and the traceless symmetric part is just this symmetric anisotropic exchange. Okay, so this was the model we used to describe this iron double layer on a tungsten. Okay, and this is the experimental evidence. This is a spin polarized STM on the system. Here we can see the topography of on the upper left corner. And if we increase, this is the spin polarized picture. We can see these stripes. It belongs to a domain wall, and in that case, the orientation of the magnetization is just perpendicular to the plane. So the STM tip was sensitive to the normal to plane orientation of the magnetization. If we further increase the temperature, this stripes disappears because the system turns into the plane. And if we decrease back the temperature, the stripes will appear again, indicating that we have a normal to plane orientation of the magnetization. So there is a temperature-driven reorientation in the case of the iron double layer on tungsten 110. Okay, we made a simple simulation. Well, in that case, we calculated all the exchange couplings and anisotropy parameters from first principles. So we have more than 2,000 exchange couplings, which was a tensor couplings, and we have all the anisotropy parameters. I here denoted some of the DM vectors, the most important DM vectors we can have. Yeah, they are all in the plane and they are parallel to the x-axis, which is in our case it's a 1 - 1 0 direction. And we got this result. If we include, so if we simulate the full model, including the Jaushinski-Morier interaction, for the anisotropy energy, we got the change of the sign at a temperature about 350 Kelvin. We got the transition temperature at 450 Kelvin, which is close to the experimental result. We got the transition temperature a little bit higher than the experimental. We got it about 350 Kelvin, and in the experiment it was, well, about 200 Kelvin. And if we do the same simulation, omitting the Jaushinski-Morier interaction, we got the black curve, and in that case there is no reorientation. So we conclude, okay, this curve is just the difference between the two, the anisotrope energy with and without Jaushinski-Morier interaction. So we conclude that in order to have the experimentally detected temperature-driven reorientation in the case of the iron double layer on tungsten, we need to include the Jaushinski-Morier interaction, which have an impact on the magnetic anisotropy through the magnetic fluctuations. And I think I have no more time, so thank you for your attention.